So yeah, the subject of the talk is privacy integrated queries. It's, as we'll see, a language for programming with privacy. If there are questions along the way, do feel free to interrupt, and we can try to drill down. We'll be introducing differential privacy and stuff, and if it's confusing and chin scratching, we'll want to spend enough time on it to make sure people are comfortable with it. Alrighty, the name hopefully will make sense as we go along. It's not obvious why you would call something this, but hopefully it'll make sense. So I'm going to start with my take, just to get some context set up on the sort of brief history of privacy, specifically privacy-preserving data analysis. So privacy is a very, very big sphere. We're going to be talking in this talk just about people analyzing data sets that may contain sensitive information, and sort of warm you up to what motivated the work in the context of previous work that got on. So we generally like to think that there's a data set. It's got some nice valuable information in it. It's probably sensitive. There's an analyst who has some sort of skill or expertise, and society has said that this is a good idea for these two to get together. We'd like to apply what the analyst knows to the data set and all of the good stuff therein. But people agree that there should be some sort of boundary between these. We don't really want the analyst to go and look at all of the data and come back remembering everything they've seen, whatnot. They should have access to the data, but possibly through some sort of porous boundary that doesn't allows conclusions perhaps to come back, but not specifics, something like that. Something that will protect the data set from potentially malicious or too curious analyst. Oops. So the first approach, this problem's been around for a while. Of course, we have the Census Bureau going back 100 plus years. The first approach that's relatively easy to think about is, what if the data provider were to take their data set and reduce it somehow, maybe aggregate some of the data, maybe scrub out some of the apparently sensitive fields, get rid of credit card numbers and social security numbers or something like that, and hand that to the analyst, who is then free to do whatever they like with what they see. This has some nice properties. It has some bad properties. So it has the nice property that the data provider gets to see what they're going to disclose to the analyst. They get to OK it first, and then they don't really need to think too hard about what the analyst is going to do with it. Right? The analyst could be malicious. They could be incompetent. Who knows? And it doesn't really matter. The privacy guarantees have already been enacted by the data provider when they distilled down the data. Now, the downside is that, of course, the analyst sort of intentionally doesn't get access to the full rich data set. They have to work with something that's been reduced potentially substantially in quality. If you've gotten rid of all the social security numbers or all the medical histories, they're not able to play with this information anymore. They may not be able to find the conclusions they're hoping to find about the data. So that's a little too bad for the analyst, I guess. Different approach. The sort of control goes the other way. The analyst submits an analysis essentially to the data set, and this can take some different forms. Programs, for example, the analyst could write a program and send it to the data provider. Realistically, actually, with the Census Bureau, the professor will send a graduate student to the Census Bureau for a summer or something like that. And at the end of it, the graduate student writes up their findings. The Census Bureau looks at them. If they're right, the conclusions then are passed back to the analyst. So the actual analysis, the thinking, did get to see the real raw data, and that's really nice and exciting. But only the results make it back to the analyst and the general public. So that's appealing. Getting to play with the actual real data is very nice. The downside here, in contrast with the other approach, is that the data provider somehow needs to trust the analyst, or needs to make sure that the process that's going on here isn't just going to report back specific information about people. That would be sort of annoying, even indirectly. But if the information that flows back is too specific, well, essentially we have privacy problems, and the data provider doesn't have a lot of control anymore without scrutinizing very carefully what's going back. So we have some good things and some bad things. I'm going to propose a new way of doing things that I'm going to assert gives us both of the good things and none of the bad things. And over the course of the talk, you guys may or may not come to agree with me. We'll see. I'll try to convince everyone, though. So the idea is we're going to introduce a new principle into the picture. So instead of just an analyst and a data set, we're going to introduce an intermediary who's going to have two roles. The intermediary is going to play the role of the data set. They're going to expose an interface which looks just like a data set, and the analyst is going to get to interact with it just as if it were a data set, and get results back as if they were interacting with the real data set. On the other hand, the intermediary is also going to provide guarantees to the data set itself that the queries that come through, the processing that actually happens, will always respect privacy. So the data provider doesn't need to worry about what the analyst is doing with the interface. the guarantees are going to be provided on its behalf. So the intent is that we get both of these good things. Analyses actually get to run against real data, and we don't really need to think too hard at all about what's actually going on in the analysis. Essentially, the layer in the middle provides these guarantees without expertise required on either part. So as we build this up, some other cool things happen, which I think are sort of new in a lot of the privacy space. So not only do we just get single analyst, single data set interaction, but you can build up ecosystems of multiple analysts interacting with multiple data sets collaboratively. This is something that in the privacy space is sort of a little scary. If you get multiple data sets, you start to be able to join data sets and intersect data sets, and this is how a lot of the bad privacy breaches happen. Likewise, multiple analysts getting together. Typically, if you go and you work with the government's data, you have to sign a nice form saying, I won't ever tell anyone else about my conclusions, at least not without going through the government first. Turns out not to be a big deal. In this case, we can support that transparently as well. All right, so that's the warm-up. Let me tell you a little bit high level about what this is. We'll get progressively more and more precise and concrete as the talk goes on. But what was this thing in the middle? So I made a lot of exciting promises. It's going to have the good thing here, good thing here. What's going on? So I want you to think of the layer in the middle as a programming language, essentially. In the same way that we have stuff like type-safe programming languages that are good to make sure that people don't screw up their computer and accidentally run off and touch memory they oughtn't on their computer. Pink is conceptually a programming language for differentially private data analysis, sort of a privacy-safe programming language. Anything that you can write in this programming language will have privacy guarantees, differential privacy, which I'll tell you about in a slide or two. On the other hand, it doesn't get in your way, so or at least that's the intent is. If you're doing things right, the program looks like a very natural declarative data analysis. I'll show you Link in just a moment. Link is, if you're familiar with SQL, it's a database-style access language for .NET applications. We'll see some examples. I think it's really nice, independent of my employer. So the gist, though, roughly is that analysts show up. They have no privacy expertise whatsoever, and they write a program that appears natural to them. They don't need to think about privacy when they're writing the program. And the computation actually, by and large, proceeds as if it would against real raw data. Let's see. I'm going to tell you about differential privacy in a slide or two, so I won't try to pitch it to you right here. The take-home message, though, is that throughout this whole process, neither the data provider nor the data analyst needs to be a privacy expert. We've sort of factored out the expertise that we've had building up differentially private computations and tried to embed it in this intermediate language. And hopefully, people get off the ground and running with this sort of thing and can actually start analyzing data sets where previously they would have been roadblocked by the lack of expertise. I don't want to suggest that privacy expertise is not helpful in using this type of programming language. In the same way that understanding what a computer does is good for programming a computer. You can write more or less privacy-efficient algorithms. You can write good programs and bad programs. They won't violate the privacy properties, but they may not be very useful without a little bit of expertise. OK. So what I'm going to show you next, let's see. The plan is to show you a little bit of Link, and in so doing, hopefully illuminate some of the concerns we might have about privacy. And then, with this in mind, try to figure out how might we actually provide privacy guarantees. So this is a big example from Link. If you don't know Link, don't worry about it too much. I'll paraphrase what's going on here. The gist is that it's a declarative data parallel programming language. So we talk about large collections, and we're going to start with this collection, this thing called a queryable, of search records, let's say. So this is an actual data set that I lifted from Bing. Lots of exciting, sensitive information in here, in particular IP addresses and search terms that people have issued against the query engine. All that we're going to do here now is take this big collection and restrict it. We're only going to look at those records where someone is queried for cricket. We're going to take all of the searches for cricket and collate them by the user ID and only keep those users who've asked for cricket at least 5 times. That seems relatively arbitrary. Notice that this grouping that's going on here, collating by user ID, is the sort of thing that got AOL into trouble. I don't know if people remember this. The data release that individually it didn't look like any one particular record was especially damning. Names were removed and that sort of thing. But the ability to collate by user ID revealed a little too much about some of the people in the data set. So this is an operation that's normally relatively scary for for people thinking about privacy. Similarly, the ability to join multiple data sets. So we're going to take our collection of people who searched for cricket a lot and using the IP address, join against another data set that maps IP addresses to zip codes in this example. Joining is also relatively terrifying. This is the process of taking multiple data sets and finding linking records based on common attributes. Something that, again, got some privacy research up off the ground. Kane Nimity and LaTonya Sweeney's work was based on the observation that two independent data sets that might appear to be privacy insensitive when linked this way start to reveal all sorts of sensitive information, health information in that case. And then the example continues. It's not hugely important at this point. We find zip codes that have at least 10 people in them. And then we're going to write to the screen how many zip codes out there actually have a lot of people searching for cricket. So this is just a program. There's no privacy guarantees anywhere in this. This is just what you would write if you were sitting down at your computer writing a link program. And the natural question that someone's going to have to face is, I wrote this program. Is it OK for me to run this on your data set? Here it is. This is all that I want to do. Are you concerned or not? Should we go ahead and do this analysis? It'll have some societal benefit. I don't know if it'll have any harm. And hopefully, people are a little concerned about this. It's not entirely clear why there would be privacy guarantees here. Will this unintentionally reveal specifics about people in the data set? It's not at all clear. So we'll return to this example a few times. One natural question, though, is in what sense we think that we'd want to preserve privacy. How can we even describe privacy of individuals in this data set? It's there are all these funny things going on. Search queries, IP addresses, lots of things someone could be concerned about with respect to their presence in the data set. So with that in mind, we'll return to the example in a bit. With that in mind, we're going to introduce the privacy definition we're going to use in this work, differential privacy. If you've seen it before, excellent. Has anyone seen differential privacy before? Anyone? Several? Many people. OK. Hooray. So I'll walk through the high-level points. The formula is not the exciting, important part of the definition. Sorry, it's the only part of the definition, of course. But the intuition about what the definition is guaranteeing is what I'd like to leave you guys with, which is that a computation, we're going to think of it as being differentially private or privacy respecting in some sense, if it has this property that when I run the computation on two inputs that are essentially identical, they differ only in, for example, your record. So think about running the computation on the full data set and the data set where you removed your record and we don't get to see it. Such a randomized computation is going to be differentially private if the probability of any possible outcome on these two worlds is essentially the same. We're allowed a little bit of a slop factor, here this e to the epsilon, which allows probabilities to increase a little bit, not very much. So e to the epsilon for small epsilon is sort of 1 plus epsilon. So a small multiplicative increase in events. But the claim is roughly that anything that might happen when we run a differentially private computation on a data set is essentially no more likely to happen than had we run it on the data set without your record. And we'll take that to be the baseline for what privacy can we give you. Well, the best we could have done would be to have removed your record, opted you out of the data set. We're essentially going to perform a computation which nothing is substantially more likely. No consequence at all of the computation is more likely with your record than it was without. So this has a lot of really nice properties. Let me highlight a few of them. They're going to be important going forward. The sort of robustness of the definition is going to make it really easy to use in a general setting like programming. So one important thing is we've made no mention so far of attackers. We haven't modeled attackers. We haven't attempted to limit what they might know or how they might draw inferences about people. So this is especially important in programming, where we don't actually know what a person is going to do with results that might come back. So if someone goes and performs a differentially private computation and then takes the results and runs off and does something with them, their program continues. We don't really know what happens. This more or less says we don't really need to worry about it. The definition is agnostic to the data type. So we just talked about the presence and absence of records. A lot of other privacy work will start by categorizing the attributes as either being sensitive or insensitive. Your name is not necessarily sensitive, but your medical history is sensitive, and these types of things. This gets very complicated as soon as you have data types more advanced than tuples. Right? If you have a string which concatenates together your name and your medical history and also has your doctor's notes or something like that, everything basically turns into this big mash of sensitive data. And we're just going to say, it doesn't matter actually, present or absent in the data set is what we'll guarantee. Finally, it's formal. And of course, we like formal guarantees. That's appealing generally. Makes us a lot happier and more comfortable making something available if they're formal guarantees. It has the additional exciting property here that with formalism, we actually have a solid basis for extension. So we can produce new computations, things that we might not have intuitively felt comfortable with, as long as we can assure ourselves that they satisfy the guarantees. So that's going to be sort of appealing. We're going to see some new things show up in this language that previously were sort of anathema to privacy. And yet, since we can prove things about them, we feel comfortable turning them on. Now, arguably, so differential privacy has been, I think, fairly successful, certainly in the theoretical computer science land. Mathematicians with PhDs have found it very pleasant to sit down and work with. Arguably, it has been tricky to use. It's sort of subtle. It's very easy to produce something that is not differentially private. And it's not always obvious when you do produce an algorithm that you've successfully convinced yourself and others that differential privacy exists. Now, going forward, what I'm going to claim is that Pink, this new programming language, is actually going to make this one of the easiest privacy definitions to use. That the robustness here means that if we, in implementing Pink and restricting ourselves to a good language, get things right, then there's almost nothing for the programmer to worry about. The person actually designing the algorithm isn't being trusted with making the program correct and respect differential privacy. And as a consequence, it's very easy to achieve. That's the hope. And you guys can definitely start raising your hands with funny comments as soon as I show you how easy it's going to be. So the plan for the next few slides, I'm going to take LINQ. I'm going to walk through what I think are the three main ingredients in LINQ and try to adapt them to differential privacy. And at the end of this, we'll hold in our hands the subset of LINQ that I think is acceptable for differential privacy, and we'll call that our analysis language, and I'll start to show you what that means that we can do. So one of the things that LINQ allows you to do, one of the fundamental operations, is aggregation. If you have a big data set, you can ask, how many records are there in the data set? Or what is the average of some function of records in the data set, or the median, or all sorts of computations that take a large data set and distill it down to some compact, manageable, non-data set typed aggregate. And what I'm going to show you now is just the example of counting. But there are a lot of simple aggregations that we already know how to do with differential privacy. That's sort of the message here. But let's walk through an example just so I can convince you. So counting the number of records, this is the size of data. With the addition of Laplace noise, parameter 1 over epsilon. Laplace noise is, you sort of see it in the picture here. It's this distribution that tapers off where the probability is decreased at a factor of e to the epsilon with every unit step away from the correct answer. So this is a nice distribution. It's exponentially concentrated. You're not very likely to be very far away from the true answer. And also, I assert, it gives differential privacy when we apply it to functions like count that can only change by 1 when a single record changes. Now, why is that? So we think of two curves here. The data without me in blue and with my record in mustard or orange, whatever that is. When I look at the probability, the change in probability of any particular outcome, let's say 105, when I add the record, the ratio between the two probabilities there, here and here, are actually just the same as the ratio, just in the blue curve, between 105 and 104. I think I got that right. Yes. And the probability distribution, the Laplace, was picked so that it would decrease at a sufficiently modest rate that the ratio of probabilities is bounded everywhere. So, and then you can get differential privacy by integration, essentially. For any subset S of these outcomes, since everywhere pointwise they're bounded in ratio, the integrals, of course, also going to be bounded. So lots of simple things that you can do. Sort of highlighted some mean, median, order statistics, stuff like that work out just great. We're actually just going to stick with count. A lot of statistics work great just with count. Fundamentally, you're looking at densities of distributions and stuff. The other functions certainly are useful, but for the rest of the talk, I'm just going to think about count. Of course, there are a lot of other sort of more complicated differentially private computations people have put together. You read papers on differential privacy, and people are assembling very complicated algorithms and then proving from first principles that they have differential privacy as a property. With this work, we're going to try to encourage people to the extent possible, rethink these analyses and try to re-explain them as simple aggregations layered on top of the next element in the programming language. So we're going to try to produce a language that serves as the proof of differential privacy, rather than having people write a complicated program and have a parallel complicated proof for why it works. So, alrighty. People, does this click for people counting with noise? Excellent. I assume at some point everyone's going to be properly sated, and there'll be no more food in the mouth, and then everyone will have questions, right? And we'll have to roll back 10 slides. But feel free to ask if anything is funny, or if you think I've done a very bad job of explaining something. These are fine comments to make. All right. The second ingredient in LINQ is the transformation. So taking one data set and fiddling with it somehow and producing a second data set. So we have examples of this where I throw away all records that don't contain the query cricket, for example. Or I do this collation by user ID, where I take a whole bunch of records that have a user ID, and I flop them into groups now where I have at most one user ID, one occurrence of each user ID, and the list of records that were connected to them. These are examples of transformations, and we might wonder what transformations are actually appropriate to use in the context of differential privacy. And here is at least one class of transformation that is fine. So I'm going to call a transformation stable, or C-stable, if it has the property that it doesn't amplify differences in data sets especially much when I apply the transformation. So if I think of two data sets A and B that have a certain symmetric difference, when I apply the transformation, I get the transformed A and transformed B. If the symmetric difference hasn't grown by more than a factor of C, I'll call this C-stable. Now, the motivation here is that if I apply a transformation that's stable and then follow it with a differentially private aggregation, the differentially private aggregation will hide differences in the transformed data. And as a consequence of this inequality, will also hide differences in the source data. So differential privacy guarantees made of transformed data propagate back to the source data as well. Now, they get worse by this factor of C, so we have to pay a little bit of attention. But generally speaking, we'll see a lot of C's that look like 1 or 2 or infinity. So those are sort of the three classes we're going to see. And this is a proof. It's nothing surprising. So the motivation for this, transformations. Why transformations? What's exciting there? Aggregations are really cool and useful, but there are only so many ways you can put an aggregation together, right? If you have count, you have sum, and you have average, and someone gives you a data set, there are three things that you can do with it. You can report each of these aggregates, and then you sort of sit and think. There aren't really a lot of exciting ways to combine these aggregates together. But transformations actually start to look like a programming language. I can start taking a collection of these primitive transformations and putting them together in arbitrary orders, clever patterns that essentially unbounded, other than the accumulation of these C terms.
Is there a notion of a fold in the theorem that would say characterize the function
For aggregation. So it's a little dicey. So the bad thing that happens with a general fold is, let's say I write a fold that looks at the current aggregate. So it says keep a number going on that we're going to accumulate with, and if it's 0, keep it 0 until we see Frank's data in the data set. Then start incrementing it by 1 as soon as we see Frank's data in the data set. And that, if I'm present in the data set, that's going to end up with n over 2 or some big value. And if I'm not, it'll be 0. So there's a sense in which we'd like aggregates to have the property that the presence or absence of any one record tweaks the total by at most 1, something constant like that. And this is a little tricky to verify for a general fold. In Pink, we've restricted it to a sort of independent sums, essentially. You can apply an arbitrary function to each record, but then we're just going to add them all up. And that's not fully general. There are definitely some things where you'd rather do something slightly different, like take the absolute value of. That's a very simple example that doesn't actually look like the sum of some stuff. But there's some neat work going on. Jason Reed and Benjamin Pierce have a paper that is trying to essentially look at a type system, sort of like linear types, that constrain how much could a function, non-expensive functions, and what function, how can I write functions that are provably not going to take small changes in the input and explode them all over the place. So that's the space of things that we know how to prove would fit in this is growing. Probably hasn't actually reached the things that are complete, though. And so I don't know if that was a good answer or not. But sorry, a fold is sort of a general form of an aggregation, unless I'm screwing up my list. You have a big data set. Think of it as a list, and you have a function that is capable of taking a current aggregate and the current record that you're looking at and producing a new aggregate. You can sort of slide down the list, updating the aggregate as you run along. So count is a very simple example of this, but there are sort of messier ones that get you into trouble because you get to look at your history in some sense. All right. Let me show you some examples of transformations just so that we can see what I'm talking about here and get some example stability constants floating around. So these are lifted straight out of LINQ, and in fact, most of the design of Pink is just me going through LINQ and saying yes, 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 no, yes, yes. So it wasn't especially hard, and that's good because it means for other languages you could probably do something fairly similar if you don't much care for LINQ. But here are two examples. So we have the where method and the select method. Where is a restriction. It takes a predicate and returns the subset of the data satisfying that predicate. Select is a record-by-record transformation, so it takes a function and returns the data set containing the application of the function to every record. And with the appropriate amount of head scratching, we can confirm that each of these, if I were to change the input to the where or to the select by one record, the change to the output is at most the consequence of that record. So if I add a new record, it might show up in the output of the where, and if I add a new record to the select, it will show up as the output of that function value. So these will have stability 1. That's great. That means we can apply these as many times as we like without hampering the privacy implications of subsequent downstream analyses. Here's a slightly more complicated function. This is something that, again, this is what got AOL into trouble before, the grouping operation that allows you to take a large set of records, identify some key. So there's a key function over here. It takes individual records in the data set and produces something like a user ID or some other key object. And the output type is essentially a collation by this key. So it contains all of the keys that we saw in the data set. And for each key, the list of records that map to that key. So user ID is a great example of this, where we want to put searches together based on the person that searched for them. And now we can apply things like a select or a where to the entire collection of searches that a person did at a time. So this is a little bit more subtle. If I change an input to the group by, I potentially change two output groups. There's a group that the element left when I made the change. Right, so it used to be in some group before I went and changed it. It's left that group and it's entered some other group. So two objects have changed. We think in our heads, well, but they changed in a special way, which was removal and introduction. But they're totally different objects. Select, when we apply it in the future, doesn't necessarily care about the fact that these were structured changes. They're potentially arbitrary alterations. So we get a factor of 2. Showing up here, the stability is 2, and this is actually correct. You can write programs that have just a chain of group bys, and the stability grows by factors of 2 to the c, and you can actually do really naughty inference if with just a limited number of group bys. So you can definitely break differential privacy by applying this too much. But it's nice to have it in the language when we do need it with the bounded influence. All right. Join is another exciting thing, very important in a lot of relational computations, database-style computations. Let me describe what it's supposed to do first, and I'll explain why I'm not going to tell you any more about it. So join is a binary transformation. Binary transformations generally aren't annoying. There are things like concat and union that we're totally comfortable supporting. So it's not the binary nature of join that's a problem. It takes two inputs. Let's call them the left and the right input, and two key selection functions, one for the left and one for the right. And its intent is that for every record from the left and right that match based on the key, we'll output that pair, essentially. So that's join. Join is, of course, very, very useful. But from a privacy point of view, it's a little dangerous, right? If I have a data set that may contain my record or not, let's just say it's either empty or has my record, and on the one hand, and I have the yellow pages on the other hand, and I do a join between the two of them where I use the key true or something like that, then my medical history, if it exists, is going to get splatted over every single record in the yellow pages and multiplied arbitrarily, and there's going to be no sensitivity bound that results from that. So that's a little annoying. It turns out that there are some stable versions of join that are not any weaker in terms of expressive power, but they are more structured in how they represent their output. So, for example, if the first thing that we do to both of these inputs, the left and the right table, are to apply a group by, where we use these key selection functions. So we first of all say, okay, everyone who matches, within each table, we're going to collate people by the key that we intend to match between the two tables for. So there's now exactly one representative for each key. Then we do the join. This ends up with a stability of 2 for each of the inputs. Now it's structured the outputs so that the whole of the yellow pages is now just in a single record. And that might be a little annoying if you're hoping to count it and see a big number at the end. You'll see sort of 1 plus or minus some noise. But we have gotten stability bounds in place. So that's sort of nice. We've taken something that previously didn't have stability bounds. We wouldn't have been able to use it anyhow, and produce something that's slightly more restricted, or substantially more restricted, depending on what you wanted to do, but comes with stability bounds. Now, a lot of cases in database land, you're doing joins on unique keys and such like that. So we are mapping user ID information from one database keyed by the user information to a second database where we also have user information. So in those cases, things work out just fine. There's no problems. There are definitely several computations, though, where this very much gets in the way, and that's too bad. But we weren't going to get privacy guarantees anyhow for the original program. Alrighty. The third ingredient is enumeration. So you can take one of these data sets and say, OK, now that I've done all this transformation, let me see the data. Start showing me actual records in the data set. And this is really easy. We're just not going to do that. We're going to turn that off. We're going to say, sorry, you can do as much transformation aggregation as you like, but you don't get to look at the underlying records. We know absolutely nothing about the privacy properties of individual records, and you just don't get to see them. All right, so returning to this example from way back when, I'm not going to run through it again, but I do want to show you what changes when we cast this into pink. 2 things are going to change. So we changed the type of this data set. So it used to be this iQueryable type, which was a general object that you could ask any question at all about, you could enumerate, you could do lots of fun things with. We're going to turn it into our restricted data type, which has only the transformations we know are stable, has only these aggregations that we know have differential privacy, and doesn't let you enumerate anything. But it does support the same interface, so your program stays the same. And for those operations that we support, the semantics are essentially identical. Again, with the slight exception of join, which in this particular case I've finessed to actually work out right. But yeah, otherwise everything else works exactly as LINQ intends. The other change down here is that when we do our aggregations, we need to specify a level of accuracy. So this is the intended epsilon of the epsilon differential privacy with respect to this data set here, popular zips data set. And of course, because of all these stability constants, the privacy implications for this data set from this count may reflect differently on the actual source data sets that we have, the query log and the IP and zip data sets that we're participating. So we need to think about how much privacy did we actually burn away from these source data sets. And that's mostly where the machinery of pink comes in, the actual implementation and stuff that it needs to do as it computes. So I'm just going to show some pictures, a little bit of a sketch of what actually goes into making pink work and what does the implementation look like. But what's it doing? Why is this non-trivial? Yeah.
On the previous slide, the epsilon that's put in there, is that a specification of how much accuracy you want or how much privacy?
Yeah, I'm sorry. So I think of them as the same. It's the epsilon that would give the guarantee of epsilon differential privacy to this immediate data set. So if I put in a 0 here, it would be 0 differentially private, by which we mean 0 accurate. The noise would be unbounded in each direction. More realistically, we think 0.1 or something like that. But 0.1 differential privacy with respect to this data set may, and indeed will, actually turn into sort of 0.8 differential privacy for one of the source data sets. And because we've done various group bys and joins and other such funny business.
Oh, I see. So you specify the differential privacy for this popular zips?
Yes. Yes. It may have multiplied a bunch. And what we need to do, and I'm sorry, we'll see in the next example, is the participating data sets need to be able to confirm that this is OK with them.
I see.
Right. So the analyst doesn't have control over the data sets. They don't get to demand full, unfettered access to all of the data sets. But they do, for reasons of sanity, they do get to specify, if they were to get an answer back, how should it be distributed? I need something accurate to within plus or minus 10. Please either give me an answer or tell me no.
OK, so the programmer does know that this will be, the error that's here will be Laplace noise.
Right.
One over the zips.
Yep. If it comes back, that's what it will be. And it may, as we'll sort of see, that one of the participating data sets has the opportunity to say, no, this is beyond what I'm willing to do. Sorry. So statically, absolutely, the programmer certainly could have statically gone, and this is really all the reasoning Pink is going to do, is statically go through and determine, before the query is actually executed, what are the privacy implications for each of the participants, verify them, and then actually run that if necessary, yeah. Yep. So that's one of the very nice properties of differential privacy, is that computations have privacy independent of the actual data set they're running on. So you can determine a priori, is this going to be OK to run or not? And quantitatively, how bad is it going to be? Alrighty. So just real quick, it's not too complicated, but there are a bunch of cute pictures that I made. So each of these Pink queryable objects has two things in it. It has this data set, which is just like we would have had if we didn't care about privacy. And it has a handy little agent object as well. And this is essentially a delegate that's going to be able to field requests for further decrements to the privacy. So if someone comes along and says, I need epsilon more units of privacy out of you, this is the little bit of logic that's intended to respond positively or negatively, accepting or rejecting that. So here's just a sketch of one way that you could implement this. One of these little agents, which just manages a budget, is coded up so that when you come in with epsilon, it tests to make sure that there's at least epsilon remaining in the budget. And if not, tells you to take a hike. Otherwise, decrements the budget and returns true. This is great. This means that, in particular, if we do a query directly against this data set, and we are like a count, we just need to check with the agent, see if epsilon is all right. We also, this is an important bug early on, we have to test that epsilon is non-negative. If you sort of track through the logic and see what happens if epsilon were negative, it's hilarious. So it basically just increments the budget. But moreover, it increments the budget. And since the noise is symmetric, it doesn't really matter that it was negative at all. And you get positive epsilon as your anyhow, that was fixed. So if the test passes, we just run the count using the link provider. So using the actual infrastructure that has already been deployed for the data set. You have a big SQL install or something like that, or you're running on dry link, which is several hundred computers in a cluster. Great, we use that. We're not going to have parallel infrastructure. That's sort of important. But before the answer comes back, we just tweak it with our Laplace noise. And transformations sort of follow the logic that we've defined. If you do a transformation, we just produce a new object, new Pink variable here, where we wire up the input with the logic applied to the data set, create a new agent that references the agent down there and scales up requests to epsilon by this stability constant. We also give the Pink agent the opportunity to clean up the expression. Right? So at this point, the expression coming in, it would be nice if it were functional, but this is .NET, so your logic for the predicate testing could be, if open a network port and transmit the data to this address, then true. And .NET will, of course, try to do this, and bad things will happen. So we give folks the opportunity to try to purify this. This is mostly, to be honest, my incompetence at actually doing this type of analysis on my own. So I'm not really a language person, and would much rather have some other serious language people come and figure out how to purify link expressions for me. Group by, basically the same. The only difference here really is that there's a 2.0 instead of a 1.0. So, alrighty. I think in the interest of time, so I would normally, we'd walk back up through this example again. I'd point at each of the group bys and say 2.0, and we'd count them all up together and see that everything is working out right. But I think that's not too exciting. 8 against the source data and 4 against the IP and zip data set. So I sort of actually, this is, I think, a cute point. This IP and zip data set is not actually, it's a real data set. Microsoft has it. We bought it from someone. It's not specifically privacy sensitive, but it is proprietary. So it's valuable to the data provider in the same way that they don't want the records flopping all over the internet. They're comfortable giving access to them in some protected way, but they'd rather not disclose them, essentially. So the same technology that gives privacy has this potential to sort of serve for proprietary data as well, give people analytic level access to it without actually showing them the specifics of each of these records that presumably have some sort of value to the company. That's random aside. There's a bit of logic that Pink uses underneath it. these are properties of differential privacy, not something that is true specifically about pink, but that it's important for pink to adapt and respect properly. This is just the sequential composition rules for differential privacy. If I take a differentially private computation, run it, look at the output, and then take a second differentially private computation and run that, the epsilon values only add up. And it's very easy to see that they only add up if these were independent computations. It's also true if there's this sequential dependence in there. All that this really means, practically, is that this step was really important down here. So that when we repeatedly test for additional epsilon, we need to make sure to think cumulatively about all the epsilons that have gone through. We could ignore it. We don't have to have that logic in there if we want to have a very permissive agent. But realistically, it's good to think of the accumulated privacy costs. There's this other neat form of composition that differential privacy has. I call it parallel composition, but the intuition is that if you have a big data set and you analyze structurally disjoint subsets, so for example, we go and count the number of men and the number of women in a particular data set, and we know or we decide a priori that that's disjoint, then the privacy costs, even though we've done 2 analyses here, the privacy costs don't add. We take the maximum of the 2. So this is the case for structurally disjoint queries. And that's sort of what this says in here, that if we can split the data set a priori into multiple different groups, we're allowed to run these computations and only pay the largest of the privacy costs. So to that end, there's this operation we introduce into Pink over Link. So Link didn't need to worry about this because, of course, Link doesn't really care about privacy. But in Pink, we introduce this partition operation, which allows us to do this explicitly. You specify some set of keys and a partition function, and returns a collection of these Pink variables. So we sort of shatter the data set into multiple pieces, each of which we can analyze, and each of which sort of the logic is coded up to only bother the agent responsible for the source data as the maximum of the cost change. So whereas previously, for example, we took these zip codes and we counted how many zip codes have at least 10 people searching for cricket in them. This is a similar but importantly different computation that takes this data set of zip codes, shatters it by zip code, essentially. So we say for each of the zip codes, give me a separate data set containing those records with the associated zip code. And I'm going to count each of them independently. So now I get some sort of estimate for each of the zip codes of how many people in that zip code are searching for cricket. And that tells me a little bit about the distribution of cricket interest by zip codes. It's different than counting, though, the number of zip codes that have strictly greater than 10 people. Just different outcomes. Neither one is a particularly wonderful estimate for the other, generally speaking, but this is very useful in a lot of cases. Yeah, I'm sorry. Yes. So the important thing that's going on here, the set of keys. Yeah, we define ahead of time what are the set of keys we expect. The computation is not going to correct us. So if there were zip codes we forgot about, it's not going to jump up and down and say, hey, you don't forget about this one that I saw in the data. So it's going to silently throw them on the floor. Similarly, if there's zip codes that actually have no one in the data set, we accidentally put in the zip code FFFFF or something like that. It's just going to say, here you go. There are some people in there, and there may not actually be any records, of course, in the data set. So this is just tweaking this example, putting this in. I guess I was supposed to save that spiel about zip codes for this particular example. So one of the things that's really cool about this as a programming language is that I can do something like this. So in all of the previous cases, we actually saw the whole program sitting in front of us. We could actually look at it, and we could collectively as a group say, I see what you're doing there. OK, I understand what's going to happen. Realistically, this isn't how programs get written. People write nice little modules that get invoked, and the implementation of this, the definition, is somewhere else that may not even exist yet at this point. Nonetheless, since we've done things in this particular way, we've wrapped up the data in this Pink variable, and we've treated it as this capability. So any access through this interface will respect differential privacy at the appropriate levels. We don't need to know what this method does at the moment. We don't need to understand it or analyze it or worry anything about it. It's very helpful for modular software development, third-party software development. If I am some person who wants to sell access to this method because I was very clever and it's worth several $100s of research or something, great, I can do that. I don't have to show you what it looks like before you can decide if it's OK to run. This is what it looks like. These are sort of green. I don't know if you can really see them here. This is a distribution on virtual Earth of people who searched for cricket in these particular search logs. And there's a cute differentially private computation that I wrote that produces this distribution. And you might worry, just looking at this, wow, I don't really think there's a lot of privacy there. I see lots of very specific dots, and if you were to zoom in, it'd be exact latitudes and longitudes. But differential privacy is not a consequence of the output. It's not looking at the output and seeing what is it. It's a property of the computation that produced the output. And hopefully I've assured you so far that Pink is doing a good job of monitoring and tracking how the computation proceeds and making sure that in that way the production of this particular output wasn't violating differential privacy. The actual algorithm that's going on here is just very smartly counting things. So it's sort of counting how many records are there in North America, and the number comes back quite large. And so you say, great, let me further subdivide North America into a bunch of subparts. I'll count each of those, and I'll continue drilling down until the counts dip below noise level, at which point I will just assign, within however big that region is, just assign the points there more or less randomly. But this does a great job of finding London for you, for example, or finding Delhi. And the southern US, we think that the southern US, this is a different sort of cricket. This is the noisy sort of cricket, not a friend of mine tried to convince me there are a lot of Indian expats in the south, and I think it's different. But right. So the program doesn't understand ocean versus land, right? So it just counts things, and it turned out, fortunately, that when we did the lower hemisphere count, that number came back really boring. So it didn't bother allocating anyone to the lower hemisphere. But yeah, random places out in the Indian Ocean or where have you are a consequence of it saying what's the count there, and the number comes back and it says 3, which is noise, and it doesn't know any better. So yeah, it flops some random point down there, and you can absolutely make it a lot smarter if you want, putting more domain knowledge in and sort of prettying things up. But the whole logic for this is about a screen full or so, and trying to keep it simple. All right, I will try to wind down. There's a picture here. I think this is probably a little complicated to go into, but I think it's sort of cute. The example over 3 slides of cumulative density functions, which is some nice way of visualizing data that you might happen to have. And the example is meant to show that there are several different ways that you can write the same computation. So there's 3 different ways of writing cumulative density function. I'll do the 2 easy ones, and then I'll just skip I'll show you how complicated the third one is, and can try to convince you that it's smart because it's complicated. So one easy way to compute the cumulative density function, so I want to know how many records are there below each value of x from, let's say, 0 up to some maximum value, is just to ask that many questions. Run through and say, for each value that I'm interested in, restrict the data set by that value, count all of the records there, and report that number. And if we want to do this, we're doing lots and lots of counts against the same data set, so we need to shade our value of epsilon by however many queries we intend to apply so that we don't overrun the budget epsilon. I've done this a priori. Pink will let you write this without the division by maximum, but you might start getting exceptions relatively soon. So this is a sort of programmer level intelligence to make this actually run to completion as opposed to just stop after the 3rd or 4th value of x. A different way we could use it is to try to do this disjoint querying thing that we were talking about. So take your values 0 up to maximum, make each of them a bucket, basically. Throw records into the bucket that they correspond to. Count each of the buckets and take the running totals across these noisy counts. And this has the nice property that the noise sort of cancels as we go along. So by the end of all the buckets in the running sum, we have error that's sort of accurate to within square root of this maximum quantity, whereas the previous one was getting error linear in maximum. So that's sort of cute and appealing, and they have the same privacy cost, same signature, all that stuff. And there's a third way, which is even more exciting, and the short version of this is that the error ends up looking like log to the 3/2 maximum because of some clever recursive whatnots where essentially we hybridize the two and don't just take buckets of unit size, but buckets of exponentially increasing sizes, and we pick the right sized buckets and stitch them together so we only ever use logarithmically many buckets. And it's clever and all of that. So, but the main point here is that this is all algorithmic cleverness at this point. This isn't fancy privacy analysis math cleverness anymore. This is just a person writing a clever program using a publicly declared cost model. Instead of running time, we're worried about this privacy expenditure, which follows a few simple rules in terms of the partition and sequential composition and stuff like that. So here are some pictures. These are the 3 curves for, this is response time onto network traces or something like that. Zooming in a little bit, the blue one is this first class of measurement that is just very irresponsible and adds a lot of noise. And the other two essentially are indistinguishable and very accurate, and life is great. So main message here is, I guess, that when you're thinking about writing programs, thinking about the best way to conduct the analysis you want to do is non-trivial. There are several different ways you could do it, and you could think about how do I really tease out the information that I want most effectively. So I'm going to wind down, I think, with this. Here's a list of some stuff that I've done with Pink. I think this certainly used to be true, and I think it's pretty close to true that I've probably implemented more differentially private analyses than the rest of the world put together, is my theory. These things are really easy to bang out and actually produce. I'll show you some examples in just a slide, but let me, well, roughly you can see machine learning, very natural. There's lots of statistical properties of machine learning. You're basically doing counting. Things are inherently robust by the needs of machine learning to generalize and what have you. Some recent work on social networking analysis. So this is a very hot topic, both from a privacy point of view, but also from a data analysis point of view. Doesn't fit exactly in with a lot of the previous models where you assume a distribution over individual records or something like this. There's these complicated dependencies. And then a bunch of random things. We had a paper recently on network trace analysis. So the goal here was to try to show that real-world applications. So there's some machine learning traces down in here, but really they're very sensitive to particular properties of network traces, and you really need to embed a bunch of domain knowledge in there. So we got together with a domain expert and produced a bunch of these and reproduced a lot of networking research that people had done in the past. So just to flip through things, I'm just trying to convince you guys that this really isn't complicated, then I'll stop. This is linear regression. If anyone knows anything about linear regression, it's not super complicated. The only interesting thing is that we're computing a covariance matrix, and that's just a sum. So there is some smarts in here, but it's almost all matrix inversion smarts as opposed to differential privacy measurement smarts. Logistic regression, lots of gradient following. Gradients in these data sets are nice big summations over lots of records. And it just happens that the log logistic gradient function is bounded -1 to 1 everywhere, so we can add them all up pleasantly. K-means clustering. So a lot of these programs are very short, very concise, and very pleasant, and they, through the program, make clear why the analysis has the privacy properties. So I like these are also the simplest things you could possibly imagine doing. They get harder from this point on, but I did want to show you that they don't have to be terrifying and complicated, and they are slightly more advanced than just counting. But all right, last slide. So Pink was this trustworthy platform for doing differentially private computation. It's available. You can go and download it, play with it. There are a bunch of demos, there's tutorial, all sorts of stuff like that. So in principle, you can actually go and use it. There are several caveats that you probably have to click through when you download it, more or less saying that it's not my fault if it doesn't actually work. But in principle, everything's available and up for public scrutiny. So you can look at it and say, actually, I've learned that this doesn't work. Please fix it. And that might happen. The main exciting contributions here really is that we've factored out a lot of the privacy expertise from the programming process. So whereas previously we needed someone to be around, privacy expert to supervise the analysis, development, deployment, everything. Now we potentially need a little bit of smarts in writing the algorithm, but from that point on, maintaining the algorithm, actually implementing it, all sorts of other concerns. We really don't need privacy people around. And any normal person off the street with an undergraduate programming education can hopefully get up to speed and write programs here. There's a bunch of new stuff. This is mostly exciting vis-a-vis previous privacy research, so stuff like group by and join, which were previously total antigens for privacy. The ability to play with raw data, so unstructured data that's just raw binary globs or strings, unformatted text, stuff like that. And modular design, giving privacy guarantees where we really don't have whole program knowledge. We don't know what's going to happen with the data, but still being able to give guarantees going forward. There are 3 things that I think are really cool for people to do next, and they appeal to different people, so I think that's great. I like the idea of privacy as this new computational resource. So we know in computer science how to write programs under a lot of constraints. So running time, power, memory, all sorts of stuff like that. Privacy, in this particular case, differential privacy, is another computational resource that gets consumed, and you can think about more and less efficient algorithms. And different ways of computing things that previously were indistinguishable because you didn't really care, took the same running time, but now, for example, reveal a lot less about the specifics of the data. I like the idea of people doing privacy research in Pink. So there's a lot of work on privacy that you see. It's a little tricky to tease apart what's actually new in our understanding of privacy and what's a new clever algorithmic development. And using Pink helps tease that apart a little bit. If you can build on primitives that people have used before and explain what's the new algorithm you've come up with, this is great and makes things a lot clearer. On the other hand, if you come up with a new primitive that we don't know how to implement in Pink, that's also exciting and interesting and possibly worth folding in the future. And then finally, of course, just getting non-experts up and running. So people who are experts in something, but not privacy. Experts in public policy or in social policy or finance or who knows what, up and running and actually doing the analyses that they know how to do, but without having to burden them with privacy is, I hope, something that's going to be cool and fruitful going forward. We're sort of at that stage now where I'm trying to find these people and shake them and taunt them with data sets that they might have access to. But anyhow, that's all. I'm done. Thanks for the attention. If there are questions, happy to take them. Oh, sorry. Thank you. Yes.
Microsoft has this thing called Health Vault.
Yes. See, I have to consult my press manual here. Hold on.
What would be involved in convincing folks at Microsoft or outside or whatever that this would be a useful tool for analyzing the data in that in a secure way?
So I think a lot of people certainly believe that. Sorry, repeat the question here for the benefit of. So there's Microsoft Health Vault, and generally speaking, a lot of Google Health also, and people, the government collecting lots of exciting information about people. There's a primary use associated with that, which is intended to be getting information to doctors when needed, or helping you, track your weight and health, biometrics and stuff like that. There's definitely also a very valuable secondary use, which is preventative care, for example. And believe the Obama administration has said this is going to be one of the big cost reductions going forward for healthcare. So we're going to do a lot of preventative care, a lot of analysis of data. And without something like privacy, that's not going to get off the ground, really, of course. You're going to try to analyze everyone's data to see what are the leading indicators of some embarrassing illness or something. And if it turns out the leading indicator is being named Frank McSherry, this is going to be awkward for a lot of people. Sorry. So convincing people, right? So I think people generally agree that it would be good to have technology, like hypothetically, something like Pink, in place that would allow non-experts to get off the ground. I think mostly what we need at the moment are people with free cycles. So a lot of these processes are just getting off the ground. They're just getting into a state where they can actually deliver the information in sub-second time to doctors. You don't want security updates to be being installed while you're trying to determine if the person's allergic to something as you're operating on them. So getting to a point where there are free cycles, and then probably doing some case studies and making sure that the level of accuracy that we get out of this is actually valuable and useful for people doing the research. If it turns out that the utility that they're hoping to tease out of this is totally killed by the noise that's introduced, then there's no point running it in the first place. Privacy is great, but you might as well just not look at the data because we're not going to be especially helpful there. There already are a lot of situations where hospitals are releasing data and sharing data using things like k-anonymity. We would argue that that's a little iffy and dicey from a privacy guarantee point of view. It has the really appealing property, though. So one of the big downsides, I guess, for something like Pink and differential privacy is that you need to have existing computational infrastructure that someone's going to manage. You can't just do some processing on your data and put it on a web page and let everyone download it and say, don't worry, it's private. Great. You actually need to keep a compute system up and running, keep the data around in its pure form somewhere, hopefully behind a whole bunch of firewalls and what have you. But there's some risk and some costs associated with that. So I think it's a very good fit, is the short answer. Hopefully, we'll see that going forward. I can make no promises about release dates or anything. Yeah.
One of the things you mentioned is that to really have these guarantees in the strong sense, we need to be decrementing the budget of each query you run. So what do you think the Census Bureau should do?
That's a great question. So in the context of a lot of public use data, there is not, the census people get very upset when you hear about epsilons that go down and eventually they say no. census data is meant to be public use, available for everyone. You're not supposed to turn off access to it at any point. There are a lot of, we've described this very interactive process where in principle every person is coming with their own queries that they want answers to, and then they go away. You can certainly design something where a batch of queries, for example, are run by a census analyst or something, and then made publicly available. So right now what the census does is essentially a lot of histogram counts. So they read out 4 people with the following 3 attributes. Here are the counts broken out, all of the different ways that we know, gender, zip code, whatever majigger. We'll report on all these counts. We won't tell you about counts that are too small, which is sort of analogous to saying we're going to add a little bit of noise to them, and if they end up below signal level, sorry about that. But you can imagine absolutely a battery of questions that go up much like the census does right now that are simply run through something like this to guarantee differential privacy, which has the nice property that sort of, well, let's see, a few nice properties. They don't need to worry about what that does. They have people employed full-time right now, 40 hours a week, just looking at what they're planning on doing next year and determining if the world is going to blow up because of their next releases. And this would make the math very clear. These people would be able to sit on the beach drinking pina coladas and live happy, long lives. Another thing that this does, though, is provide, so the failure mode for the census in terms of access is someone writes a petition to them and says, I can't get what I need out of your statistics. I would like to look at all of your data, please. Or a large chunk of your data. And this is essentially the only recourse that they have. And they don't have to let people get access, but the only other thing that they know how to do is essentially bring people in, either potentially remotely by computers, but give them access to the data set and make them sign a bunch of forms. And this is a slightly more principled way of accomplishing a subset of those goals, at least. There are things people would like to do with the whole data set this wouldn't let them do, but principled ways now of letting social scientists actually get in there and look at the data. But I don't know if that was a good answer or not. So Lil.
So maybe it's somewhat related. So there are these recent works like the multiplicative weights mechanism and so on. These differentially private algorithms where somehow people can show that the privacy hit is much smaller than the number of count queries made.
Yes.
And in some sense, maybe it feels like you did something similar with when you did the recursive cumulative CDF.
Yep.
Do you have a way of emulating any of that kind of reasoning?
Yes, fortunately. So yes and no. So not emulating the reasoning. So what Salil's referring to is there's a bunch of papers that are built out of the same sort of primitives, counting and such, but the analysis is not, let's just add everything up, nor is it, let's take the maximum. It's something slightly more clever and subtle as you go along. And what I spend a lot of my time doing, and it's actually quite fun, is looking at these sorts of papers and really trying to tease out what went on, what was the important observation from the query that really got us the good information and minimized the privacy costs. So for example, with the multiplicative weights paper, this Hart and Rothblum paper from Stock, was it? Or Fox. Oh, wow, okay. From Fox just recently. They make lots of noisy counts, but argue that, well, really only a few of these are actually important. Most of them are pretty boring and uninformative, and we won't worry about that. Moritz and I recently played around with this and actually just found a way to directly pull out what are the interesting queries. So there's this neat primitive in Pink called the exponential mechanism that allows you to point at something and say, essentially give me a noisy argmax. Give me something that nearly maximizes some function. And it's a great way of sort of blindly going and picking a really delicious answer to something that you might have looked at a whole large collection of a lot of different count queries or something like that. It'll find the right one for you to measure in a differentially private way. So there are a lot of research in trying to take algorithms that we know work and know have differential privacy, but recast them into, I use Pink in particular, but into some sort of language like this, both to sort out if something new has really been discovered and also to tease out if there are weaknesses in Pink that I can fix. But there have been a lot of success with this. There are almost certainly some, but I'm not really sure of a lot of them that can't be recast. But Greg.
So is anybody using it?
Well, I'm using it. What? Actual product groups or something, or.
What would you tell them when they say, well, what should we set at the
So everyone asks this. So the real story is that this whole epsilon setting is a very natural question. What should I set epsilon to? And Pink was invented because I didn't want to keep getting asked this question over and over again, because I don't know the answer, is the short answer. But what I think the correct response is that it really does depend on how sensitive is the data and how useful is the analysis that you're going to do. And it's a discussion that the analyst and the provider will want to have. Now, I can't completely excuse myself from it because neither of the two participants know what epsilon means. But fundamentally, if someone goes to a medical data set and says, I'm doing a survey on shoe size, I need to look at your HIV records, presumably the epsilon value that gets put together there is going to be different than if someone says, I need to look at your shoe records and I'm going to cure.
But I mean, do you think you could go, say, to and talk to those guys who do have experience choosing whether to release something
Yeah.
and negotiate a reasonable epsilon for a given?
So I think it's a really interesting question. I don't know the right answer. I think, yes, some progress could be made on this. I don't know that it's... So we have some good mathematical intuition for what it means in terms of the increase in risk and stuff like that. I think realistically it's going to involve sitting down and actually thinking about what is... let's try it this way. Let's see what epsilon would you actually need to accomplish the same levels of accuracy as previous releases, this type of thing. And then sort out, does epsilon actually translate into real harm? That's something that statisticians like to think about. What's the actual harm that goes on? You've changed the distribution a little bit, but that's different than showing people your medical records. As we start to do analyses with various values of epsilon, if we can see that nothing bad is actually happening, we might allow a little bit more epsilon to seep out and be comfortable, as long as we manage things that way. So the short answer is there's no magical thing for how should you pick epsilon. I equate it sort of with how much is your time worth or something like that. It's how much is secrecy about your personal information worth? Well, it really depends on what it's going to be used for and what specific information we're talking about and a lot of stuff like that. But the only reason it's a question at all now is because we actually have this nice quantitative definition of privacy. And previously, people would talk briefly about what should K be in K-anonymity, and then everyone said 5, and they were done. But no, it's a good question to have, and you can actually do cost-benefit types of trade-off now. That getting 5 more units of accuracy out would cost me this much more in terms of privacy. Let's actually think about, is that worth it or not? What are the implications? And hopefully I can get some other people together to figure that out while I'm off having my pina coladas on the beach. But yeah.
So you mentioned social networking. I hope this question is vague, but in social networking, there are classes of queries you might want to ask that are very hard to describe given the kind of relational sort of syntax that you've shown here. For example, if I want to find all people who are related by a particular kind of path with social
Sure.
people who are, 6th degree dating friends, it's very hard to express that using a,
It turns out it's 6 joins, if you want that.
Yeah.
Or 5 joins, actually, right? Because,
You can imagine a more complicated problem.
yes.
Very
Yes.
I'm wondering if you think, is this something that's genuinely hard to write a differential privacy aware language for? Since it's a different,
Right.
problem, it's different topology, or is it just someone needs to go in?
So it's not. It's definitely not the latter. So it's not that we know how to do this, and it's just a matter of running out and doing it. There are definitely avenues that you could attempt to take. So you could take something. So instead of SQL or LINQ, you could take something like datalog, which has these nice recursive queries in it, or XPath, I guess, or something like this, and try to adapt differential privacy to them. Social networks and a lot of the things that you were just talking about do have this annoyance, though, that single edges, presence or absence in the graph, which is sort of the smallest privacy atom that people are usually willing to talk about, the existence of a friendship relation between people. If we're starting to talk about long paths, they can break a whole bunch of links. If I have a bunch of 2 cliques, right, and I just throw a single edge in between them, I've created a whole bunch now of people at 6 degrees that didn't used to exist before. So that particular statistic is probably just going to break. And essentially for good reason, right? This wouldn't have been differentially private, at least, to reveal these sorts of specifics. But there are similar quantities that you can try to get at. You can weight a lot of these paths. So if everyone's using the exact same edge, you can downweight the counts, essentially, in ways that will actually give you differential privacy. It's less easily interpreted in terms of what did I actually just count. But there are some things you can do that can help to tease out a little bit of connectivity information in the network. Is it well partitioned? or not. Pink doesn't do a very good job at this at the moment because it's wedded to these discrete records. But sort of Pink 2.0, which is underway, has these sort of more fractional notions of presence and absence. So it's ongoing research, absolutely. I think one of the main messages from the Pink project, at least, though, is not specifically that this is a great language, but thinking about making languages differentially private, or finding an analysis language that fits and gives you the guarantee of differential privacy is a good thing to do, because then you can invoke the social networking analysts who actually know what they want to compute, as opposed to having a bunch of theoreticians sort of postulate that the most exciting thing is certainly whether there's a bichromatic K5-4 in the graph, because that's because we had that one figured out. And there was another question. Yeah.
I was just going to ask, have you been doing any work, or have other people been doing work on trying to think about the externality of mode when, I write my program in an inefficient way, and therefore the future analyst or
Right.
will execute their program,
Right.
and somehow we could introduce some kind of market regime
So this makes a lot of sense.
to your system to handle that problem?
So one of my favorite ways of doing things. So the question is, what if? How do we deal with or worry about people who might write inefficient queries, thereby consuming essentially a shared resource between everyone? There are a few answers to this. One, the simple one is, everyone should get their own budget. There should be quotas. There should be some sort of rate control, so that it's a little tricky to determine if someone is actually wasting everyone's time. I'm really interested in shoe sizes, and I'm going to spend a lot of privacy budget looking at shoe sizes. The rest of the world may think that's foolish and a waste of time, but I think it's great, and convincing me otherwise is going to be difficult. So putting in some sort of policy level that regulates how quickly can people burn away different levels of privacy, or some sort of fair sharing or something like this that goes along would be interesting. Privacy does have this problem that once it's consumed, it's consumed. So if you give me a budget and I use it, I can't change my mind and give it back. And yeah, absolutely. So the outputs are shared. You can certainly economize by, if I went and did a count, I could then sell that count to other people. Or before I give you access to this count, I want from you half of the privacy budget that went into producing it. You could definitely try to do something like this. We certainly haven't thought hard about the game theoretic implications of this. Who should actually go and do the query in the first place, or whatnot. But there are definitely ways of getting multiple people to coordinate and collaborate slightly more effectively than you just give them each their own budget, or you give them all access to the same central pool of budget. Yeah. Yes.
So into what epsilon should you choose, can you run this in some mode where instead of saying yes or no, it'll just tell you what the epsilon should be?
Yes. Oh, tell you what it should be. Sorry, you mean think of how much budget is left, and then find it for you? So I tried to stay with, so that's a very natural question. What if you have 5 units of epsilon left, and you just want to do one count as accurately as possible? Couldn't you just go and do that? And the answer is yes, you definitely could. In fact, you could actually, the programmer, figure out what the right value of epsilon is. I didn't want to have build that into Pink's functionality. You could certainly build that on top. Slightly related, there's a mode that I usually run Pink in, which just prints to the screen values of epsilon as they get. It always says yes. So it's a totally fine auditing tool at the same time, right? That if you don't actually want to interfere with the analysts, they did have access to the data, but you want to track who's out there screwing up privacy for everyone. This is definitely one way of doing it. It'll keep track of in exactly the same way of who's burning what epsilon, but it doesn't at any point tell you no or see budgets go negative or anything like that. But the ability to sort of reverse engineer, figure out what the right epsilon is, you could certainly do sort of by yourself or a layer on top of. There are many layers you could put on top of Pink. So that's sort of one thing that a lot of people ask, couldn't I have this functionality? A lot of the database people are really interested in query optimization. So you have a big complicated query or multiple people doing queries, and you might like to refactor it and make it more efficient, or do an optimization-y type thing. And absolutely, someone else should do that on top. Someone who knows more about that sort of thing should do it. A helpful suite that helps people get the most out of their data is definitely something. If you find the right epsilon, it's definitely something that's would be useful and is not part of what's here. But you guys can fight for it or something.
Again, if you have sort of multiple people accessing the same data set, sometimes
Yes, yes.
Do you have any way of dealing with
There's nothing built into Pink. So one thing you can definitely do, you're absolutely right, is you can retrospectively think about the queries that have been issued. So someone went and counted the number of men in the data set, and then someone else went and counted the number of women in the data set. And retrospectively, you could say, well, okay, those were disjoint. Let me essentially refund a little bit of privacy cost. So you certainly could do that. I don't have a great story for how to do that at the moment. It's a little bit of program analysis. I mean, that particular example, we hypothesized that there were these disjoint classes, men and women, and gender studies people might tell you that this isn't right. And this domain knowledge was sort of flippantly introduced and possibly not actually true. But if you can actually get people and find scenarios where really there are these hard constraints that certain subpopulations are disjoint, like by looking at actual numbers and their actual greater than, less than signs involved or something, you can, after the fact, go back and say, yes, great, the privacy cost was indeed much lower. Let's hand some privacy money back to people. Or in the same spirit, do this multi-query optimization where 5 people are coming in with questions, and you might rethink. Everyone wants to know something about the total minus their the deviation of their subpopulation from the total. Let me compute the total once, share it out between everyone, and then essentially lower everyone's individual privacy cost because we shared something out. Yes, is the answer to whatever the question was. So
how hard is it to get people to write programs that are robust to the kind of errors that are introduced? So, for example,
good question.
Two counts could be inconsistent with each other.
Yeah.
And in practice, does it turn out that most ways people would write programs will generally be robust to that? Or
so it's a good question. So definitely when you run these sorts of programs, you might do a count, and you might expect to see integral results return, for example. You might just expect to see non-negative results come back. And it's not going to be the case for Pink. And there are definitely programs that I've written, even, that mysteriously get NANs and infinities in them, which I think are probably related to these sorts of issues. So it's not trivial, I think, is the short answer. A lot of the reporting that people do, the very simple sort of, let me do some counts and print to the screen, this hasn't been a huge problem. The numbers that come back, if they are negative, people sort out mentally. Oh, I understand what happened. Great. But yeah, certainly as soon as you start folding noise into multiple levels of computation, or doing logic and conditionals based off of these sorts of counts, funny, slightly counterintuitive things can happen. It's really easy to write programs that branch indefinitely because you thought that when you took a data set and partitioned into 2 parts and counted, it would be the same as up here, and that eventually some of them should get to 0 because they're also discrete. But it's really easy to write some nice branching process that finds 4 subpopulations, and as long as one is non-negative, continues. Strictly positive, continues, and bad things happen in that program. Yeah?
So you use them constantly as something that's support. Is there a way to have
Absolutely not. Absolutely not. So, right. Unfortunately, no. On account of if you have compact support, you have regions of 0 probability, and if the data were to slide, if I were to add a few records and cause them to now have non-zero probability, with differential privacy as defined here, there would be, go from 0 probability to non-zero probability, and that's an unbounded multiplicative increase. There are relaxations of differential privacy that allow an additive term as well. That's meant to be much, much, much smaller. So an additive term on the order of sort of 2 to the negative 1,000 or something like, incredibly small, which allows you to transition from 0 to non-zero. And when I think the definition is fine. I don't think there's any problem with having infinite support. But
what if the data sets naturally have limits? Like, I mean, you don't have unbounded numbers in what the count would be.
Right. That's fine. I mean, all that we've done is given you a noisy observation about the true data.
But an infinite noise, meaning that you know it possibly can't die higher than 25, and then there's of course, it says your noise distribution could have a false value of 300,000. That's not going to be meaningful.
So essentially you're saying that your domain knowledge is going to be screwed out of
you are allowed to take the noisy result and then
Truncate it to 25 if you want. Yeah. That's totally fine operation for you to do. And if you as a reasoner want to apply that sort of reasoning, yeah, whoa, I see that it's more than 25. I know that that can't happen. Let me think slightly differently about what the truth must have been. Totally fine. You'll do the exact same reasoning with the same probability as whether anyone's record is present or absent in the data set. So privacy isn't going to get compromised in this setting. But any sort of post-processing you want to do to try to essentially reverse engineer what the data might have been given the noisy observation that you made, or that we made for you, is totally welcome. It turns out, I mean, that the Bayes optimal thing to do is to figure out the true posterior over the data set given your prior. And if your prior has zeros in it, if you say nothing can be negative, nothing can be bigger than 25, your posterior will also have zeros there. But differential privacy will still be respected. And
It's 1 o'clock, so we should thank you for
excellent. Thank you.